All right. Good afternoon, everyone, or good morning, or hello, everyone. In this lecture, we're going to be going a little bit deeper into intermolecular forces. Now, what we previously talked about were intramolecular forces. Now, these are different compared to our intermolecular forces. Now, the forces that are between molecules. So I always like to find a molecule, and I'll like to say this one and this one. These are two separate molecules, three, four, we have five independent molecules. Now, I always kind of like to think about like a population. These are individual molecules in a population. Now, they are going to interact with one another. Now, the forces that exist between them are relatively weak. If we compare that, however, or sorry, when we compare that, we're comparing it to something like a covalent bond, which is what we spent a good bit of time talking about in preparation for a previous exam. If you remember, we talked about like electronegativity. When we talked about a covalent bond, we talked about polar covalent, non-polar covalent, and so on. So basically you could say that what we've previously talked about are intramolecular forces. Now, those intramolecular forces are fairly strong. Now, the physical state depends on intermolecular forces, which seems a little bit counterintuitive, maybe it's a little bit counterintuitive, but this question or this statement right here says, is something a solid, a liquid, or a gas? And that question is answered when we look at the intermolecular forces. So these weaker forces are ultimately what dictate if something is a solid, liquid, or a gas. Now, keep in mind that these basically are saying, is that thing held together as a solid? Is it held together, or is that substance, is that sample, extract, whatever you want to say, is it held together, or all of the molecules there holding it together strong enough to make it a solid, a liquid, or a gas? Now, dry ice, which is what we will see here. Oh, I had that in the PowerPoint. Let's see if I can get that going. No, that's not what it's supposed to do. Okay, what I'm going to do is I'm going to share my screen to that browser. So here what we have is dry ice sublimating. Someone's picked up a piece of dry ice, which maybe, and we're going to drop it directly into uh, water. Now, what's going on here is, or there's a couple of things going on here. One thing is that if you look at this um, on the right-hand side right here, that dry ice in the atmosphere, well, that's going to turn to a gas. If we look at the on the left-hand side here, well, we're seeing that dry ice very rapidly go from a solid to a gas in a process known as sublimate. Now, the reason that they did it in water was, well, this water is warmer than the ambient temperature, and it's basically able to kind of provide a lot of or provide a lot of surface area and be in contact with. So this is an example of dry ice, carbon dioxide, solid carbon dioxide going from a solid to a gas. Now, whenever we're talking about these different types of uh, intermolecular forces, well, they have different strengths. So we have our weakest intermolecular forces, our strongest intermolecular forces. Now, these dispersion Forces are also known as London dispersion forces. They're also called LDF. They're also called induced dipoles. Now, this type of force is going to exist between any and every single molecule. But the strength of those interactions, so essentially what this is saying that A and B, molecules A and B are going to come in contact with one another, and they are going to have dispersion forces that hold them together. A molecules A and C will also have dispersion forces between them. B and C will have dispersion forces between them. The dispersion forces between A and C might be slightly stronger than A and B, which might be stronger than B and C. Now, the thing is, all three of these are so weak that it's important to recognize that they're all kind of in this lower tier. I always kind of liken it to something like, well, I'll use it as an example. Um, let's take the best high school basketball team. That best high school basketball team, yeah, they might be great, but by virtue of their kind of like age and experience, they're never going to be as strong as another extreme end of this uh, level of forces. They're never going to beat, you know, again, not the Lakers, the Celtics. They're not going to beat the Celtics because they are just in separate leagues altogether. So these dispersion forces, some can be stronger than others. The best high school basketball team is better than the second best high school basketball team, which is better than the third best high school basketball team. But they're not going to be kind of in competition with the other levels or the other tiers of intermolecular forces. So our next tier of intermolecular forces are known as dipole-dipole interactions. This is where two molecules, well, they both have partial charges. So if we were to look at something like water, now water is kind of a tricky one, but here's a water molecule. Lone pairs of electrons, that gives the top half of this a partial negative charge, and then the bottom half of it a partial positive charge. Well, if we had another hydroxide or water molecule, sorry, here and here, well, this water molecule also has a partial negative charge, and this has a partial positive charge. The partial negative and partial positive charges are going to kind of get in close proximity to one another. They're going to align with one another. Um, and they're going to be attracted to one another because of that. Now, our third tier of intermolecular forces or type of bonding is hydrogen bonding. Now, this is only going to take place with one part, you got to have a hydrogen. The other part, that hydrogen is going to have a covalent bond to oxygen, nitrogen, or fluorine. So when you see a hydrogen bond, you need to see something like O and H. So O and H, let's go with CH3. There we go, CH3OH. And then let's go with another CH3OH. This oxygen here has a lone pair of electrons. This one also has a lone pair of electrons. Now, this hydrogen bond that can be established is always going to be represented like this. I'm going to clear all my writing here so that I can highlight my hydrogen bond. My hydrogen bond is right here, or it's right here, or it's right here, or it's right here. These are all hydrogen bonds. Hydrogen bonds are denoted by a dashed line. So when we see OH, well, this can form a hydrogen bond with that oxygen. What about this hydrogen? Could it form a hydrogen bond with another oxygen? Yeah, and boom, there it goes. Now, I want to contrast that with what people have a tendency to make a mistake on is they hear about hydrogen bonding and they say, aha, I know hydrogen bonding. That is where I have a hydrogen. So then they say something like, that's a hydrogen bond. Carbon to hydrogen, that's a hydrogen bond. That is incorrect. When you are looking for hydrogen bonding, you have to have an oxygen, a nitrogen, or a fluorine, and a hydrogen. Now, these are the three types of intermolecular forces, three major types of intermolecular forces, and they range from the weakest to the strongest. We're going to focus on dispersion, dipole-dipole, and hydrogen bonding. Now, these have an increase in strength as we move from the left-hand side to the right-hand side. What that means is that this is going to increase melting and boiling points. So think about this as the weaker the intermolecular forces are, the more flammable, the more volatile, the more easily a substance will boil. So if you had a substance, if you had two substances, one was held together by hydrogen bonding and the other was stabilized by dispersion forces, which one is going to have a higher boiling point? The one that's held together by hydrogen bonding. You're going to have to put more energy in to disrupt that, what we see here, this network of hydrogen bonds. This network of hydrogen bonds stabilizes this. And so this is why when you have a dense network of hydrogen bonds, that's why when you think about something like, doing a cannonball or doing a belly flop into the pool, well, it's that hydrogen bonding that really makes it unpleasant for you to land directly on your belly. Okay, so now here what we have is which substance has the highest boiling point? Okay, we've got methane, ethane, and propane. And you can already see that the C is highlighted. And I have to do one thing. Now, we've got this one highlighted, but let's go ahead and talk about why. Okay, so methane, ethane, and propane, these are compounds that are known as hydrocarbons. So that means all that they have is here's methane. Great, awesome. Here's ethane. Oh yeah, second carbon. Cool. And then last but not least, some of y'all are probably recognizing a trend here, and you are correct. As hydrocarbons, they have nothing but carbon and hydrogen. Boom, 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 boom. Okay, so we have one methane molecule. Let's say these two molecules get in close proximity together. Let's talk about our interactions that exist. Well, do either of these molecules, either of these methanes, have a pole, have a positive or a negative charge? They don't. So no dipole, no dipole, dipole. Okay. Do they have any sort of hydrogen bonding? Let's see. We need a hydrogen, right? Yeah. Okay. So they got a hydrogen. Do we have an oxygen, nitrogen, or a fluorine? I always like to just say enough. Do they have enough nitrogen, oxygen, or fluorine? They don't. So no H bonding. Okay, so that's out. Then what do they have left? Well, they have that induced dipole, those dispersion forces. Dispersion only. They have dispersion only. Then the question is, well, methane and another methane, why is their boiling point seemingly the lowest? Well, it has to do with the overall size of these molecules. So we throw out another H. See, these individual components of these molecules, they will interact and they will stabilize their interactions, in which case our boiling point or a physical property like our boiling point is going to increase. Next up, we've got is which substance has the lowest boiling point? Okay, so here what we're looking at is now what we're being asked is which substance has the lowest boiling point? Okay, so low BP means weak interactions. Okay, now if we used what we learned on the previous slide where the largest molecules had the strongest interactions, which gave us the highest boiling point, then what do we have here? We have Cl2, Br2, I2. Which one is going to have the lowest boiling point? Well, the one that has the weakest interactions. Which one's going to have the weakest interactions? The one that has the smallest molecular weight, or the smallest average atomic mass of 35.45 AMU. Okay, now what we also have to worry about and be thoughtful of is whether or not a molecule is polar. Okay, now which one of these has the highest boiling point? H2, HCl, methane, or methanol? Okay, now the forces that stabilize these. Okay, H2 and H2, a small molecule. Compared to anything else, that's going to be pretty low. So A is out. Okay, HCl. If we have an HCl solution, those chlorine, those chloride ions are going to be able to come in contact with one another. They're fairly large, but those are, this is an ionic compound. So those ion charges between those the charges between those ions are going to be kind of a stabilizing factor. So that's compelling, but let's see what else. Methane's on here. So HCl or methanol. I'm seeing methane on here, but if we're talking about highest boiling point, so that means it's going to have to require a lot of energy to be input in order for this substance to basically evaporate. And one of the things that we have is the types of interactions that we can stabilize and put together here. When we look at a molecule like CH4, this is what it looks like. And if we have two of those, essentially it's just CH4 versus CH4. Okay. Now let's look at this. Okay, so CH3OH. That part of these two molecules, they'll be in contact with one another. And you know what? Those will give us LDF. or London dispersion forces, or a dispersion force between them. Now, let's say that we have, and let's go ahead and switch this right here from ACH4 to CH3OH. This part of our molecule, however, is a little bit more interesting because this oxygen has lone pairs of electrons. And what do we need for hydrogen bonding? Our strongest of our intermolecular forces? We need a hydrogen. Check. That hydrogen has to be bound to an oxygen. Check. So when we have this OH in close proximity to another molecule with an OH, we can have hydrogen bonding, which gives a strong interaction, or a strong bond there. Now, what we need to be thoughtful of with respect to that is those sorts of interactions are going to have an influence on boiling point and other physical properties. Now, another thing that we're very thoughtful of and reflective of in chemistry is solutions and preparing solutions, substances that make a solution. What are those two components? So over here on the right-hand side, we've got a solution of salt water. That salt water consists of, lo and behold, water and salt. Okay, so that salt will dissolve in water and make a solution of salt water. There are other types of solutions. The more complicated they are, well, we can have a liquid solution that has a mixture of a liquid and a gas. For example, a carbonated beverage. So these little bubbles right here, they have carbon dioxide in them. We also have lots of sugary drinks. For example, here is a mixture of a liquid and a solid. What we have is essentially orange juice. So orange juice with and without a pulp, we've got small amounts of this solid sugar that it has dissolved into there. So it's a mixture of a solid and a liquid. Okay. Last but not least, an alcoholic beverage, which is a mixture of two different liquids, or it's a liquid mixture of liquids. So our solute is a liquid, which, if we go back, our solute and our solvent are liquids. Sugary beverages, our solute is a solid, in that case, sugar. And our solute for a carbonated beverage would be a gas over here. So those are all interesting and unique ways to think about solutions. Now, another important question that we always want to look at as chemists is we always want to look at whether or not a substance is going to dissolve and predicting the solubility of something. So we use this principle of like dissolves like. So will something dissolve? And we look at this in terms of a polar substance. So this goes back to our question of, is a molecule going to be polar or nonpolar? If you remember, asymmetric molecules were polar, and then symmetric molecules were nonpolar. And we always kind of looked at the electronegativity of a substance. So if a polar solute is placed in a polar solvent, then we should expect that that substance, that solute, is going to dissolve. A nonpolar solute in a nonpolar solvent. Well, this is like nonpolar solvent, then we are going to see it dissolve. An ionic solute in a polar solvent. So I want you to think about this and think about our definitions of nonpolar covalent, polar covalent, and something that was so polar that it was ionic. So ionic is just, you could kind of think about an ionic bond or an ionic substance as being so polar that it's kind of off the charts. So it is polar, but it's like extreme polar. So Ionic substances will dissolve in polar solvents. Nonpolar solutes will dissolve in nonpolar solvents. Polar solutes will dissolve in polar solvents. Now, which is not the case? Anytime that you mix any of those up. So in a polar solute will not dissolve in a nonpolar solvent. A nonpolar solute in a polar solvent. An ionic solute in a nonpolar solvent. These are, this all goes back to like dissolves like. So if you have a solute and a solvent that are different, then it's not going to dissolve. Now, which of these substances do you expect is not going to dissolve in water? Okay, so to answer this question, we have to do a couple of things. Now, I recommend that we start at the bottom. The reason I say that is because let's look at our compound, sodium nitrate. That's Na and O. That's one of those polyatomic ions, nitrate. This is an ionic compound. That's sodium nitrate right there. What that means is that each one of these substances is an ion, an ionic solute. Okay. This is this ionic? Yes, I got it right, ionic. Now, the next question is which substance does not dissolve in water? Is water our solvent? Yes. I got it right, solvent and polar. So will an ionic solvent dissolve in a polar solute? Or sorry, an ionic solute dissolve in a polar solvent? Yeah, absolutely. Okay, now let's jump back up to the top. So D is up because that will dissolve. Ammonia. What does ammonia look like? H, 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 and then a lone pair of electrons. Well, since we have asymmetry because of this lone pair of electrons right here, this is definitely a polar solute. So A is off the table. Now we've got B and C. What's the difference between these? When we were looking at B back here, they said that this was capable of hydrogen bonding. I mean, heck, you could look at it that from that perspective and say that this could hydrogen bond, but also the geometry of this. Is this going to be symmetrical or asymmetrical? Well, this is definitely asymmetrical, therefore it is going to be polar, in which case polar in a polar solute vent like water, yeah, we can cancel that out. Last but not least, we're left with hexane, which is C6H14. So 6 carbons, 14 hydrogens. Is this going to go into water very well? No, this is looks a lot like this right here, but basically these two things put together. 6 carbons, 14 hydrogens. Oh man, those hate being next to each other. They're absolutely going to hate being next to something with a positive charge or uh, a dipole like water. So C is our answer. Now, conductivity of different solutions. There are, so basically what we're looking for when we're talking about a solution is can electricity flow through it? And it's kind of interesting. Whenever I hear the phrase electricity flowing through something, for some reason, I always just visualize like someone swimming underwater. You're flowing through, you're swimming through the water. But it's a little bit different than that. The electrons that make up this electricity, they need to jump from something to something to something to something. And in a solution of pure water, there's nothing for these electrons to be shared from and to. So if we have an electron being generated right here and it's flowing, it essentially gets to the water, it gets in and just basically drowns. Sometimes if you were to do this experiment with this little light right here, it might flicker, but there's really nothing for it to, you know, conduct electricity on. So pure water is not a good conductor of electricity. Now, if we compare that to sugar water, okay, let's think about this. Sugar water. What this sugar, what this sugar is going to do is this is going to be a um, neutral compound or neutral molecule. And it's not going to conduct electricity very well because it doesn't have any like ionic compounds or ionic or ions. Meanwhile, salt water, well, what is the Na and Cl minus? Those sodium chloride ions end up in the solution throughout. And so the electrons flowing from here jump onto those individual ions so that they can be transported. So ultimately, they're going to make their way all the way through. They're going to light this light up super bright. Then they are going to continue to complete this current. And that's ultimately going to wrap it up for today. Um, I hope that was helpful, and I hope you have a good one. Bye.